My name is Simon Shim. I'm a guest editor for New Generation Memory for the Computer Special Issue. My guest here today is Mr. Alan Niebel. He's a CEO of WebFeed Research, which publishes a quarterly report on flash memory, and he's an expert in new generation of memory as well. Alan, so my first question is, can you introduce new memories, and which one is the most promising area for this new generation of memory?
I'd be glad to. I think what we're talking about is storage class memories, and those are memories that basically have the capability of almost unlimited endurance, or right technologies, has very fast access speeds. They don't necessarily have to be symmetric in terms of the same read and write speeds, but in the single nanosecond range would be most nice, and have very good retention, and they consume very little power as they are non-volatile, and they are basically will have to be bifurcated into two different areas. One will be a replacement of DRAM, or will handle the memory side of the architecture, of computing architecture, and the other side will be replacing storage, or the NAND portion of the new architectures that we have in current applications, particularly in computing, also in mobile, and then in consumer applications as well. So what we've seen to date is on the memory side, we've definitely seen SRAM and then DRAM. DRAM has come to 20 nanometer node or class memories, and we're just beginning to see some of the DRAM being produced at maybe 28 nanometers from Samsung, Micron, and possibly Hynix. But it's very difficult for it to scale much further, and we will see that there is a need for possibly one of the new technologies to maybe not have as much endurance, but will have a very good access, and will consume a lot less power than what is needed for the refresh of DRAM. Many of the vendors of DRAM are trying to go vertical with the hybrid memory cube that Micron has been had proposed, and others are following, which is basically 3D stacked DRAM, and this may work as a way to extend DRAM's capability, but it still consumes a fair amount of power, and it is volatile as well. There will be well, let me continue on with the current technologies. On the non-volatile side, we've seen flash memory has come into play since about 1990, first with NOR, and that's very good for random read access. It's very slow on its writes. It is very reliable, and it is pretty much perfect every time it's been built. The main problem with NOR is that it's getting expensive to build it at densities greater than 512 megabit Expansion has announced an 8 gigabit component, but 512 megabit, 1 gigabit, 2 gigabit, 4 gigabit, and now 8 gigabit are very expensive, but they do have a few attributes that make them viable for some small niches. And then besides NOR, we also have NAND. And NAND has grown from its infancy in 1995 all the way till this year, and we will see this year NAND revenue will be approximately somewhere in the neighborhood of I think it's about $26 billion in revenue, which is quite nice or very huge, and it has been able to scale quite nicely. We're now seeing products at 18 nanometers, and we're listening to Micron and Toshiba, SanDisk, as well as Samsung talking about going from 1Y, which is 1920 nanometers, down to 1X at 19 to 20 nanometers, and going to 1Y, which should be around 15 to 16 nanometers, and then eventually to 1Z, which would be anywhere from 10 up to 12 nanometers. And this is all horizontal or planar NAND as it gets produced on an XY dimension. NAND has been really modified with a lot of firmware and software to make it function as a storage class memory in order to have pretty fast reads, and with these controllers they've been able to manage the defects and the issues of leakage and not having too many electrons available at 19, 16, or 12 nanometers, and so keeping the charge intact has been a big problem, and laying down silicon is also a very difficult problem with polysilicon scaling beyond 1Z on a horizontal and planar basis. So many of the companies that manufacture NAND and then use NAND in controllers, particularly in SSDs, have been able to improve the computing system quite good by reducing the wait states that the old hard drive-based storage systems needed to wait for the data to come out of the storage media and into the RAM and then fed into the processor. So with the ability of having access through solid-state memory itself, we've seen the latency drop quite dramatically. We've seen the amount of data that's able to be brought into the system grow at least by about tenfold as well. And so there are now lots of modifications on the metadata, on the firmware, on the application software, and all the drivers as well, to optimize for more speed, more throughput, and better access. It is through writing in a block mode instead of a byte mode, which is preferably needed in the future, and that's where DRAM is. But when you look at the problem of using a lot of DRAM, you always get into the power budget and find that there's not a lot of additional power available to host another server, to power the DRAM and power some of the hard disk drives that need lots of volume in order to generate the amount of throughput that you can get with solid state drives, and feeding that into less amount of DRAM and into fewer servers in order to maintain the throughput or the quick access speed when somebody does a search on Google, for instance, and you can see in less than 3 or 4 microseconds you're going to get sometimes thousands of responses. And so this is what storage class memories are trying to do, is instead of using a lot of software and tricks to overcome this power draw that DRAM requires, and they're trying to write directly into the hardware just like DRAM does, but have it stored in the memory directly, so that you don't have to store it in solid state storage or magnetic storage in a hard drive, and then go through translation layers to actually to find the data, and then pull it up from the physical media, and then go through a whole stack of software to make it usable. And it will be a lot more efficient when we can just write directly into the memory and then feed it directly back into the processor when needed. So that's why there is a big push for these new storage class memories that can reduce some of these software layers and hopefully provide a very good access time. So I look at the future memories as being either able to do the memory function like the DRAM requirements are there, or to do the storage function as NAND has been able to provide. And a few years ago, IBM thought that phase change memory would be able to do both, but that was in around 2000, 2002, and thereafter. Phase change memory has had its issues, but they are looking at current volumes that they found a niche where Micron is now shipping 1 gigabit and 512 megabit phase change memory components in cell phones, replacing NOR or NAND in what was the feature phone is now the low entry smartphone. And so they're now putting 1 gigabit of phase change memory with 512 megabits of DDR2 DRAM, low power DRAM, in a multi-chip package or module, so that you can have the phase change take over the functions that either NOR or NAND was doing in the same configuration. And we're finding that yes, you can have greater endurance than flash because phase change is able to do 10 to the 6 write cycles easily. They could migrate to 10 to the 8th and maybe eventually 10 to the 12th, which is pretty good. There is a problem with phase change that they've had, and that's where if you try to pre-program it and put a charge into it and then take the chip and solder it on to the printed circuit board in your manufacturing line, that soldering process can wipe out any programming that you've done in phase change memory. So this is what caused, I think, Samsung to pull back from putting phase change in a feature phone back in 2010, I believe, where they put it in and then they had to recall the whole batch because of errors in the system. Micron has decided to change the manufacturing flow, and so they program the memory after it's been soldered on the board, and Micron claims it isn't a big cost adder, but I don't quite buy it. I've talked to other vendors, and they claim that most manufacturers like to be able to program the memory as they have with flash or mask ROM before they lay the chips down onto the circuit board. So it is a little bit of contention, and we'll see how Micron can continue with the manufacturing for the cell phone with the programming after the chips have been laid on the board. We're also hearing that Micron is trying to use phase change as the controller managing NAND flash in the cell phone on the storage side, and that's it's not a solid state drive, it's a embedded flash drive, or in a sense where you have one package with a controller, and then you can stack 1 to 16 layers of NAND flash in a BGA package and put it inside your smartphone. So Micron is attempting to try this maybe later this year or next year in replacing some of the eMMC components with phase change as a controller, and it will provide more life to the NAND and in terms of more endurance, and act as a rough scratch pad, and it also can write on a byte level, which has also been translated into the memory. So phase change still is not considered to be the front runner for real replacement of memory or storage in terms of other research that's been done with non-volatile memories. Currently we're looking at 2 other technologies that are vying for trying to pick up the memory side, and those 2 technologies are spin torque transfer MRAM, magnetic RAM, and the other one is CB RAM or RRAM, resistivity RAM. And I'll talk about the STT MRAM first, and this is magnetic RAM that is very similar in functionality as DRAM, except it doesn't use as much power. It is non-volatile, and it is currently being researched, and it has been brought into sample production through the only company that's ever manufactured MRAM in quantity, and that is Everspin, who was spun off from Freescale, which was spun off from Motorola. So Everspin is currently producing a 64 megabit STT MRAM for select customers, and they should be in mass production within 12 months from now. That's per a conference held in May of 2013, or just a few weeks ago. So they have a foot up on the other big vendors, which are Hynix and Toshiba, are in an alliance to produce STT MRAM. Samsung acquired Grandis, and they are continuing to try to build STT MRAM. Micron has a couple of programs. They are also with joint development venture with Singapore Labs to build ST MRAM. And so those are the big companies there. TSMC is also working on MRAM, STT MRAM. And then there's some smaller startups, Avalanche, Crocus. Everspin is still in that group. There used to be a company called Magsil, but they couldn't continue to work without a viable prototyping foundry, which they couldn't find. But in addition to them, there is also Magic, which is an offshoot of TDK, but they may have gone in stealth mode again. And there's a Spin Transfer Technologies, which is also in the Bay Area as another startup. So I think I've captured most of the. There are probably some more MRAM companies, but these are the major ones that I'm aware of. And then their big problem is to get the spin transfer technologies to operate correctly, and then to build it on a 300 millimeter wafer. And the tools for doing that are still in development, but they should be available by the end of the year from Lam Applied and ASML, etc. So I think that is one of the gating factors. MRAM still is much more expensive than DRAM, and it is it's still in the megabit arena, although Hynix and Toshiba and others just claim, when they bring it out, it will be in the gigabit density. So it's wait and see. I've heard next year we may see something from the big boys in terms of they're producing some ST-MRAM. So it remains as one of the most viable technologies for replacing memory in the system. Now, the other technology, which is resistivity RAM, there are three different variations of resistivity RAM. One is conducting bridge RAM, which is use a metal ion movement, and they actually create a metal filament between two diodes, and and by changing or reversing the polarity, it will ungrow the filament, and it will no longer conduct the charge, but it is a localized filament instead of across the whole surface or field effect of the cell. Now there is ReRAM, which uses a oxygen ion movement, creating an oxygen ion filament. And Panasonic has been doing quite nicely with this, and they are going to be using RRAM or ReRAM in embedded applications. So it's also a very difficult process to understand and to manufacture, but Panasonic has done quite a bit of work. Back on the CB-RAM or the metal ion filament side, the companies that have made the most progress first is Adesto, where they have actually manufactured, as of last year, a 1 megabit CB-RAM component, and they've sold tens of thousands of them in a consumer application, but they are also working with Altus and doing embedded CB-RAM. So Altus just announced that a couple months ago. So they will be competing again against Panasonic and possibly Rambus if they can find other foundries that can take on their design of embedded RRAM. So on that side, there seems to be some good traction because you can make RRAM with less layers than NOR flash, and it can scale. So it's just a question of defining what you want the RRAM to do, and then it will be able to work in terms of optimizing it for endurance or speed or low power or integration with the logic or metal in a process. So there's a variety of ways you can go with embedded ReRAM and or CB-RAM. So there's a good opportunity there. There has been a question, yes, you can make CB-RAM and ReRAM as a NOR replacement for standalone memories, and that's basically what Adesto has been doing, and they claim they need to walk before they run. And so they will start with that for a little while and continue to grow the density up much higher than what we've seen before, and it's interesting to see how they can allocate their resources. So they're developing embedded ReRAM. They're doing standalone NOR densities. They're moving towards having some of the CB-RAM being used as a DRAM replacement or to take on some of the functioning of the DRAM, maybe not the super high endurance, but at least being able to take it up to 10 to the 8th or 10 to the 10th. And Sony is also working on CB-RAM, which they've done since earlier than 2007. And Sony is also partnering with Micron on their CB-RAM. And they are also targeting the memory side of the computing architecture. So they claim they can be in gigabit densities by 2014, and I'm just coming from a point of Missouri. Show me the silicon and then we'll believe it. But they seem to be making pretty good progress as well. We've also heard about memristor from HP and Hynix, where they want to use the ReRAM and generate high density as a NAND replacement, so to speak. HP also talks about doing it in process of improving or adding some intelligence or some logic in the memristor technology. It sounds viable, plausible, but it also puts it out quite a ways away from being commercialized. But the basic memristor, we've heard rumors that the HP Hynix relationship has been very strained at the least, and it's caused them to put a delay. HP is saying, well, we've done all the work on the technology, but there's about 95% still needs to be done in terms of productization and then making it manufacturable, which is all put on Hynix's shoulders. There's some truth to that, but it's still a few years away from it. SanDisk and Toshiba have been working on a ReRAM and a 3D structure for ReRAM that they just announced at ISSCC and the International Memory Workshop. And they've developed a model of the 32 gigabit ReRAM in 3D mode, but we haven't seen the silicon yet. And if you put it in line with where they expect to build it in terms of replacing NAND, it comes after NAND goes into 3D mode. So according to their timeline, they're working on 1Y with NAND right now at 19 nanometers. And then they're going to go to 1Z, which would supposedly happen late next year or 2015. And by 2015, we will supposedly see other companies like Micron and Samsung come out with 3D NAND in production. Samsung and Toshiba claim that their 3D NAND will come out after they go to 1Z, which looks like being in production of 3D NAND would be around 2016. And so they can easily run that for another 5 years before needing to go to 3D ReRAM. So that would put ReRAM in early production, possibly in 2018 or most likely 2020, when it might get into mass production in the Toshiba SanDisk manufacturing line. So NAND really has not much to worry about for the rest of this decade. As I said earlier, it's scaling on a planar basis right now. When it gets to 1Z, SanDisk claims they will still look to see if they can shrink it beyond 10 nanometers. but they will go vertical, and that's where they're developing at a higher lithography node. I've heard as high as 40, maybe in the 30s or high 20s, where they are going to stack somewhere between 16 or 24 layers vertically, and this will allow them to achieve terabit type densities for a single chip that has many stacked layers to it. So they plan on using the same 3D structure for ReRAM, because ReRAM will scale below 10 nanometers and will have all the same attributes, if not better, in terms of write and reads and scalability and cost. And that's what Toshiba, or particularly SanDisk, believes is the roadmap for ReRAM. I personally believe that there may be some very difficult challenges going 3D NAND, and it may be that if they have difficulty getting high enough yields or getting it to function at the bare minimum speeds and endurance, that many of the manufacturers will just continue to play out the one Y and the one Z node for 3 to 4 years per node and extend that and just milk it, sort of the way that DRAM has been operating before it went from 1 to 2 gigabits in density and 2 to 4, which is slow to happen as well. That provides an opportunity for somebody to come in with another type of ReRAM that could be done on a planar basis or a cross-point array that was first established by Unity Semiconductor, but they got bought by Rambus, and that design was, a similar design was picked up by Samsung. Micron is working on it as well. There are some issues about retention. So finding a viable storage alternative to NAND seems to be a real hidden issue. Some of the ST-MRAM guys, particularly Avalanche, believe they can get the F-squared down to less than 4, maybe even 2, 2.5, and they believe that they could scale ST-MRAM to be cost effective and be multi-layer level and multi-layer and provide it as a NAND replacement. But it's more almost science fiction than reality at this point in time. There's always been a real difference between looking at a design, talking about a design, building a couple of prototypes, and manufacturing millions of components. So I fall back on what Everspin is doing, what Adesto is doing, what Micron is doing in terms of truly building silicon or storage class memories in volume production and working off that to overcome the manufacturing issues and the yield problems, and as well as the design and architecture. So those are some of the areas that I'm looking at for where these storage class memories will appear. It's very possible that Panasonic may be able to do a standalone ReRAM and do it for both memory side or the NAND or storage side. And it will depend on getting something up and running and then improving the learning curve and the manufacturability. But even if a company like Micron was to dedicate 5% of their fabs capacity to building a layered RRAM type of structure, that still would not be very much volume compared to all the production from Samsung, Toshiba, Hynix, SanDisk, and the rest of Micron. So it's definitely going to be a good 5 years before we'll see anything even having a glimmer of hope to usurp NAND as the storage technology of the future. So with that, if you have any questions, I'd be glad to answer them.
That is excellent review. I appreciate that you taking really detailed view. I had just one more question. So how does the new memory impact the computer system in the future?
It will reduce the number of layers of software. It will be able to write directly to it. It will be able to even store metadata that's in the cache, and should the cache lose power, it can store it right there in the memory itself. And being byte addressable, it will be more efficient in terms of not having to erase a whole block or a sector to just store a byte's worth of data. And it will be searchable much easier. The big question is getting to a cost that's equivalent to where NAND is today in the future, and cost is always king. So it will never replace hard drives as a low-cost storage. Well, let me say, by 2050, it might do a replacement by then, but there's a need for so much storage of all the data that's being collected. We've heard that it was 2011, there was 2 zettabytes of data stored, and probably in 2012 there was somewhere like 4. And they're saying by 2020 that there's a need for possibly 20 or 25 zettabytes. And if that's the case, we'll need every kind of storage media available, whether it's nearline, tape, optical, hard drive, or magnetic, and all the solid state that we can come up with in order to store all the data that's being collected. But the real key is, how do you access the hot data, and where are you storing that hot data, and can you keep the systems operating in real time to analyze it or recreate it in a 3D virtual reality area. And that's where storage class memories or solid state memory really makes a big impact on the throughput of the data, because that's what's needed for virtualization. You just can't do it off a hard drive. And so we'll see the systems get more integrated, more throughput, very low latencies, and well integrated with the drivers and the software, so that we can take advantage of the speed of a query or a lookup, or of grabbing a parameter, or doing an image search and recognition, and or working with voice and sound controls and projecting it onto a display. So things like the Google Glasses definitely need more and more speed and compact storage and very fast search functionality. So, that's just a part of it. But being able to share the RAM across a network or across a system, so that you can actually virtualize it and virtualize your storage, seems to be a big key. But even with all the virtualization, you still need some hardware to store stuff, because it doesn't sit out in this ethereal cloud in the sky. It still has to be grounded in some sort of storage system physically somewhere, even though you can duplicate it maybe tens of times. It still needs to reside somewhere. So we do need all the different kinds of storage just to keep track of all the data that's being generated.
Thank you very much.
Well, it's my pleasure, and I hope this will be used to promote some of the new technologies, which they do need funding. They need more minds to devote to their use. I think to combine memory and logic is the real groundwork that's going to be fully explored in the second half of this decade, and definitely in the 2020 decade. Memory and logic in the same hardware. So that's the real future, but we have to get to there from now. And so we'll see how RRAM can develop, STMRAM, maybe some phase change, and see what comes. So thank you for this opportunity.
Thank you.
All right. Bye-bye.
Bye.